Okay, so let's find the critical value z, and that's alpha divided by 2, for an 85% confidence interval. Now recall that I said we could possibly use the t-distribution table, and if I look on the t-distribution table, notice that 85% is not in here. So I actually cannot use that one, and so I'm actually going to have to calculate this one. So if I draw my normal distribution curve, and I've got 85% in the center, well, 1 minus 85%, that is going to leave me with 15% left over. Okay, so on each side down here, on these two tails, what's going to be left over is half of that. So 0.15 divided by 2, which is going to give me 0.075 on each side. And so that is what I'm going to look up in the center of my cumulative normal table to get the z-score that I'm going to use. And so if I pull up my cumulative normal table and get rid of what we were looking at previously, and I want to find 0.075. So I want to find 0.075. Well, if I look, I don't have an exact 0.075. I have 0.0764 and 0.0749. So what I'm going to do is I'm going to take the one closest to 0.075. And that one closest is 0.0749. And so the one closest to that is negative 1.44. So that's the z-score that I'm going to use, is a negative 1.44. And so I'm going to come back over here, and that's a negative 1.44 over here, and a positive 1.44 here. And so that would be the z-score that I would use on a confidence interval for an 85% level of confidence. So let's look at how we actually want to construct a confidence interval for when sigma is known, our population standard deviation. First, we want to find the value, that should say value, of the point estimate. And that point estimate in this case is x bar, our sample mean. If we don't know our sample mean, we calculate our sample mean. We'll be given that information. Then we need to find the critical value of z alpha divided by 2, corresponding to the desired confidence level, just like we have been doing. Then we want to find the standard error. That standard error is sigma divided by the square root of n, and multiply it by the critical value to obtain the margin of error. Remember that the margin of error is our z alpha divided by 2 times that standard error of sigma sigma divided by the square root of n. And so I want to find that margin of error. We want to use the point estimate and the margin of error to construct our confidence interval by saying x bar minus z alpha divided by 2 times sigma divided by the square root of n is less than the population mean, which is then less than x bar plus z alpha divided by 2 times sigma divided by the square root of n. So this is where we get that plus or minus our margin of error. Our last step is always to interpret the results. We always want to say, what do those results actually mean? So let's look at an example of this and see if we can calculate it. So a professor wants to estimate how many hours per week her students study. A simple random sample of 78 students had a mean of 15 hours of studying per week. Construct and interpret a 90% confidence interval for the mean number of hours a student studies per week. Assume that the population standard deviation is known to be 2.3 hours per week. Okay, so we know some information already. We know that we have a random sample of 78 students. So that's n is equal to 78. We have a mean of 15.0. So that's x bar is equal to 15.0. We want a confidence interval of 90%. So a 90% confidence interval. And the standard deviation is 2.3. So standard deviation of 2.3. So we know this information. The information that we need to find z alpha divided by 2. So since it's a 90%, we can use the t-distribution table and come here to the bottom. 90%, our z is 1.645. So I'm going to come back over here, and our z is going to be 1.645. Now that we know this information, we can calculate our confidence interval, because it's going to be x bar minus z alpha divided by 2 times sigma divided by the square root of n less than the population mean less than x bar plus z alpha divided by 2 times sigma divided by the square root of n. And I'm just going to substitute these values in for their appropriate values in the formula. So that's going to be 15.0 minus 1.645 times 2.3 divided by the square root of 78 less than mu less than 15.0 plus 1.645 times 2.3 divided by the square root of 78. Now the question comes into play as far as what do we round to. The rule of rounding for confidence intervals is, first of all, do not round until the very end, until your final values. But on your final values, you'll round to whatever place value your sample mean is. So our sample mean here has 1 decimal. So that's what you're going to round your final values to. So my suggestion is find your margin of error right here. Round it to 1 decimal place. Don't do any rounding with this calculation in here. Once you get this value, you can round it to 1 decimal place. So I would do the 1.645 times the 2.3 divided by the square root of 78 and round it to 1 decimal place. And when you do that, you end up getting 0.4289 and some other numbers. And since we're rounding to 1 decimal place, that comes out to 0.4. And then you can, if you notice, this is the same as this over here, so you should be adding and subtracting the exact same value on both sides. So you're going to take 15.0 minus 0.4, which is going to give you 14.6, and 15.0 plus 0.4, which will give you 15.4. Now, what it means to interpret this is to actually write out a sentence, descriptive sentence regarding these numbers and this application. And so what I would do is the professor can be 90% confident. In other words, include your percent confident that the mean amount of time, let's see, mean amount of time our students spend studying is between 14.6 and 15.4 hours per week. Notice it is descriptive. It talks about the level of confidence, what it's about, and then it includes the two numbers that you just found. Okay? Now, you can also, with confidence intervals, you can make the margin of error smaller if you're willing to reduce the level of confidence. Because the smaller the confidence level, the smaller your z value is. And therefore, that's going to make your your margin of error smaller. You can also reduce the margin of error by increasing the sample size. And how we do that is, let's look at the margin of error. That is z alpha divided by 2 times sigma divided by the square root of n. Well, with a little bit of algebraic manipulation, we can solve this for our sample size. And so that's actually going to come out to be n is equal to z alpha divided by 2 times our standard deviation divided by our margin of error, and that entire amount squared. So I would do this multiplication and division first, get a value, and square it. And so this can actually help me calculate how large of a sample size I need to get a certain margin of error. Now then, the rule here for your sample size, whatever number you get, always round up to the next whole number. So it doesn't matter if I get 3.01. I'm going to round up to 4. You always round up to the next whole number because you need that extra little bit of the number, and so you can't round down to the 3. So you always have to round up to the next whole number. So let's look at an example of this. For a psychology experiment, Emma is assigned the task of finding the mean number of hours students sleep per night. Her results must be at the 99% level of confidence, with a maximum error of 0.25 hours. Assuming the standard deviation is 1.4 hours, how many students will Emma survey? So we know that we want a maximum error of 0.25. We know that the standard deviation is 1.4, and we know that the confidence level is 99%. So we need to find, first of all, our z, alpha divided by 2, and we're looking for our sample size. So we go over to the cumulative distribution table and we say, is a 99% confidence level on this table? And it is. 99% is right here. So the Z that we're going to use is 2.576. So we're going to use a Z of 2.576. And we're going to use the formula. N is equal to Z alpha divided by 2 times sigma divided by our margin of error squared. So I'm going to use 2.576 times 1.4, not 1.6, 1.4 divided by 0.25, and I'm going to square that value. And my suggestion is to go ahead and do this multiplication and division, get that answer, and square it as of last. So 2.576 times 1.4 and divided by 0.25 is going to be 14.4256. You square that and you get 208.0979. Now notice that you have 208 and then a little bit of extra. Well, I need this little bit of extra to be accurate. So I cannot round down to 208. I actually have to round on up. So I actually need 209. So Emma needs to survey 209 students. Oh, not 208, 209. 209 students need to be surveyed. Okay, so what I want you to do is I want you to practice with finding confidence intervals where the population standard deviation is known, and practice finding the sample size. And if you have some questions, let me know.